Last time I promised, and now I'm going to deliver. Gibbs free energy. This is what we have been building up to this entire chapter. Gibbs free energy is named for a guy named Gibbs. Don't worry about him. He was an unremarkable man, even in his own life. Well, that's actually a giant lie. He was pretty impressive, but we don't care. Delta G is equal to delta H minus T delta S. That's the equation you need to remember. Gibbs free energy is equal to the enthalpy change minus temperature times the entropy change. Okay. If you're really interested, you can look that up in your textbook. But Gibbs free energy is a state function that tells you whether a process is spontaneous. If you can find the Gibbs free energy change for a process, then you know whether it's spontaneous or not. If delta G is positive, it's non-spontaneous. If delta G is negative, it's spontaneous. If it's equal to 0, it's neither spontaneous nor non-spontaneous. Okay? So negative Gibbs free energy means it's going to happen. Positive means it's not going to happen. 0 means it's at equilibrium. I'm not a huge fan, personally, of the term non-spontaneous. I prefer to use Dursley, because there's no group of people more non-spontaneous than the Dursley family. I imagine there are people out there who actually have the last name of Dursley who really hate J.K. Rowling. Anywho, what non-spontaneous really means is spontaneous in the reverse direction. Okay. If you have some process, A goes to B, where delta G is greater than 0, that means that the reverse process, B going to A, has a delta G less than 0. Okay, that's what non-spontaneous really means, is that the reverse reaction is going to happen, not the forward reaction. And delta G equals 0, of course, again, just to reiterate, means equilibrium. And now let's work through an example really quick. Okay, these sorts of problems aren't really actually difficult, just kind of tedious. You're just working through stuff that you've done before several times. Okay, so let's look at liquid water turning to gaseous water. Okay, it's the opposite of what we looked at before. So liquid water turning to gaseous water, what is the Gibbs free energy change at 90 degrees Celsius and at 110 degrees Celsius? Once again, we're going through a lot of effort to find an answer we should already know. So to find the Gibbs free energy change, we need to find the enthalpy change and the entropy change. Okay? So delta H and delta S. So we look those up in tables, and the enthalpy of formation for liquid water is negative 286.83 kilojoules per mole. The enthalpy change for gaseous water is negative 241.82 kilojoules per mole. The entropy of liquid water is 69.91 joules per Kelvin mole. And the entropy for gaseous water is 188.71 joules per Kelvin mole. So this is just a couple of Hess's law problems. The enthalpy change, the enthalpy of reaction for the vaporization of water is negative 241.82 products minus reactants minus negative 286.83, or positive 45.01 kilojoules per mole. Really quick, we stop and we look. Does this make sense? It's a positive number. That means that we're looking at an endothermic process. Yes, that makes sense. The vaporization of water is endothermic. You have to put energy in to get water to boil. And the entropy change, the entropy of reaction, is 188.71 minus 69.91, or positive 118.8 joules per Kelvin mole. And does that make sense? Yes. Going from liquid to gas, you are going to increase the entropy of your system. Boom. Okay. Those make good sense. So, the Gibbs free energy change for a process is delta H minus T delta S. So, we plug in the numbers. That's 45.01 kilojoules per mole minus temperature times 0.1188 kilojoules per Kelvin mole. Now, that is something that can trip you up. Be careful. Okay? Be very, very careful. Always be careful of your units. Entropy is reported in joules per Kelvin mole. Enthalpy is reported in kilojoules per mole. Okay? So joules and kilojoules, okay, you always are going to have to change one. I mean, the reason they do that is because the joules per Kelvin of entropy is a lot smaller. Okay? So it makes sense to report it in joules. Okay? But you either change enthalpy to joules per mole or you change entropy to kilojoules per Kelvin mole. Either way, pay attention to your units. Be careful. So, I asked for the Gibbs free energy change at two different temperatures, 90 degrees Celsius and 110 degrees Celsius. Do not forget to change those to Kelvin. That's 363.15 Kelvin and 383.15 Kelvin. So when you plug those numbers in, you do the math. At 90 degrees Celsius, the Gibbs free energy change for the vaporization of water is positive 1.867 kilojoules per mole. And at 110 degrees Celsius, the Gibbs free energy change for water is negative 0.5094 kilojoules per mole. Boom! Okay, that's the sort of answer we want to find there. A positive Gibbs free energy change is a Dursley process. It does not want to boil at 90 degrees Celsius. A negative Gibbs free energy change, a negative delta G, is a spontaneous process. At 110 degrees Celsius, yes, water will boil. Okay? So this is a way of finding a good temperature for a reaction, you know, where a reaction becomes spontaneous based upon the enthalpy and entropy for that reaction. Okay? You just say delta G is equal to 0, then you solve delta H equals T delta S. Let me go ahead and write that out for you. Okay, delta G equals delta H minus T delta S equals 0. Okay, so delta H, you just add T delta S to both sides. You get delta H equals T delta S, and then you divide both sides by delta S. T is equal to delta H over delta S. Okay, that temperature is the equilibrium temperature, where a process goes from being Dursley to being spontaneous. Okay. On one side it's non-spontaneous, on the other side it is spontaneous. For this particular reaction, delta H over delta S is 45.01 kilojoules per mole divided by 0.1188 kilojoules per Kelvin mole gets us 373.15 Kelvin or 100 degrees Celsius. All right, now let's go ahead and see if we can't get a good feel for Gibbs and the sign of Gibbs and the signs of enthalpy and entropy changes. Will a process be spontaneous? Okay, there are four possibilities based on the signs of delta H and delta S. Both positive, both negative, one positive, one negative. Okay? So, if it's an exothermic process, okay, remember, I said exothermic tends toward spontaneity, but not always, because it could be with a process that is a negative entropy process. Okay? Or you could have a positive enthalpy, which is an endothermic process, which tends toward a non-spontaneous. But you could have that paired with a process that increases entropy. So if you have an exothermic reaction that increases the entropy, okay, you're talking about a negative delta H and a positive delta S. That's when we're in the upper right-hand corner, and the process is always spontaneous. Delta G is always less than 0 for an exothermic process that increases entropy. Now, if you have an endothermic process that decreases entropy, you're looking at a positive delta H and a negative delta S. We're in the lower left-hand corner. Okay? And then delta G is greater than 0, and the process is always Dursley, always non-spontaneous. It is possible, you know, it's difficult but possible to drive a non-spontaneous reaction, to force a Dursley reaction to happen. You just have to sort of link it to something else. Like a ball rolling uphill, it's not going to roll uphill unless you roll it up the hill. Okay, you have to force it. You have to drive it. Just FYI. All right. Now, if you have a process that is endothermic but increases entropy, okay, then you are looking at something like boiling. Okay? That's going to be spontaneous at high temperatures. That's because, you look at the delta G equals delta H minus T delta S. If delta H is positive, then the T delta S term has to be more. It has to be bigger in order to overcome the endothermic nature of it. So the temperature has to be high. So in the upper left-hand corner there, endothermic processes that increase entropy are spontaneous at high temperatures. They're Dursley at low temperatures. So things don't boil at lower temperatures. They boil at higher temperatures. Conversely, and down in the lower right-hand corner, we have exothermic processes that decrease entropy. That would be something like freezing. And those are spontaneous at low temperatures. All right, now let's move on. Okay, now let's talk about equilibrium. KEQ and Gibbs free energy. Or to put it another way, Gibbs free energy, the change in Gibbs free energy versus the change in Gibbs free energy. All right. If you have nothing but reactants, your reaction is going to go forward until it reaches equilibrium. At equilibrium, delta G is equal to 0. But delta G is just based on reactants and products, right? I mean, that's just delta H minus T delta S, and that's products minus reactants. And where does equilibrium come into that? Well, we're talking about delta G with the dot versus delta G without the dot. Okay, that degree sign is important. Delta G with the degree sign means standard conditions. Okay, delta G without that degree sign means not at standard conditions. Okay, so standard conditions means 1 atmosphere and room temperature. It also means that you have 1 mole of 1 molar of everything, or 1 atmosphere of everything. Okay, so standard conditions means the concentration of everything, reactants and products, is 1 molar. Or it's if you're talking about gases, then the pressure is 1 atmosphere. And you'll see if you look down at the equation for delta G without the dot, it's equal to the delta G standard plus RT log Q. So if everything is at 1 molar or 1 atmosphere, then Q is just equal to 1, and log of 1 is 0. So that's where those numbers come from for standard conditions. Okay, so the other thing to note about this little equation is that R is the universal gas constant. Remember PV equals nRT? Well, in this case, though, the units have changed because we're talking about energy. So instead of liter atmospheres per mole Kelvin, the gas constant is 8.3145 joules per Kelvin mole. It's the same gas constant, and it comes from much the same place. But because the units have changed, the number has changed. Okay, so you're going to have to be careful with your gas constants, too. You're going to have to be careful with R. Okay. So here is the takeaway. Okay, so what happens if you have more products than reactants? Well, look at that equation. Delta G standard plus RT log Q. Okay. If you have more products than reactants, remember Q is products divided by reactants. So if it's, excuse me, my mind is blanking. Okay, so if you have more products than reactants, then you have a number that's for Q that's greater than 1. That's what that means. Log of 1 is 0, so if Q is greater than 1, that means that the log is positive, and that means delta G is positive. Okay, so because delta G standard plus RT log Q, If you have more products than reactants, then you're too far to the right. Okay. Oh. Okay. So you're making the Gibbs free energy more positive as you build up more and more products. Whereas if you have more reactants, then log of Q is a number that's less than 1. It's going to be a fraction, somewhere between 0 and 1. And therefore, log of Q is going to be a negative number, and delta G is getting smaller. So the more reactants you have, the more negative the Gibbs free energy is going to be, or the less positive, depending on the process. Okay. So, I mean, it's just directly related to what we already know. Okay? If you're left of the equilibrium, the process wants to go forward. If you're to the right of the equilibrium, the process wants to go backward. As you approach equilibrium, the process is going to slow down, because at equilibrium, delta G without the dot is equal to 0. Okay. So if delta G without the dot is equal to delta G with the dot plus RT log of Q is equal to 0, okay, remember, that means we're at equilibrium. So let's get rid of this Q and replace it with K, KEQ. Okay, we're at equilibrium. And then you just solve for delta G with the dot. You get delta G is equal to negative RT log of K. Okay. And that is the connection for us. Okay, that is the connection between, or a connection. There are a lot of connections, but that is a connection between thermodynamics and kinetics, is that delta G is equal to negative RT log of K. And I really want to show you some examples, but I've gone a little bit over, so it's going to have to wait for the next lecture.